video, we're going to be studying for my physics final by working on some practice problems, which I will be solving on my whiteboard. And although this video is not intended as a physics lesson by any means whatsoever, I'm still going to be inserting an image of the question that I'm solving in case anyone's curious as to what I'm being asked of. And as I work through the problems, I'll probably just be thinking out loud, whether it be inaudibly, audibly, unintelligibly, soft-spoken, or whatnot. So, I hope you enjoy this video, and I want to, of course, thank you for being here with me today, for joining me, for keeping me company, and this is just a little glimpse into what I do in my day-to-day life, which I know may not seem very exciting, and that's simply because it is not very exciting. But on that note, let's get started, shall we? A square coil with each side 5.0 centimeters contains 100 loops of wire and is positioned perpendicular to a uniform 0.60 Tesla magnetic field. It is quickly removed from the magnetic field. It takes 0.1 seconds for the whole coil to reach a field-free region. How much power is dissipated in the coil if its resistance is 100 ohms? I'm going to begin by writing down the given information. So we have number of turns is 100. 0 minus 1.5 times 10 to the negative third Weber. That equals negative 1.5 times 10 to the negative third Weber. Change in magnetic flux. Okay, I'm just gonna erase some stuff really quickly to make room. Now we're gonna be using the induced EMF formula to find the induced EMF, which is epsilon equals negative n change in magnetic flux divided by delta T. Plugging in the values, 100 times negative 1.5 times 10 to the negative third Weber divided by 0.1 seconds. Now plugging that into the calculator. Get 1.5 volts. We ultimately want to use the formula B dis equals I squared R to find the B dissipated. But before we do that, we have to find I, which is the current. To do that, we'll use I equals epsilon over R. Plugging in our values, we get 1.5 volts divided by 100 ohms. We get 1.5 times 10 to the negative second amperes. Making room. Now we can finally use B dis equals I squared times R. Plugging in our values, 1.5 times 10 to the negative second amperes squared times 100 ohms. Plugging that into the calculator. We get 2.3 times 10 to the negative second watts. That's our answer. Good job, everyone. The next one says two long parallel wires are separated by 20 centimeters and carry anti-parallel currents as shown in the figure below. The wire on the left is located at x equals negative 10 centimeters and carries a current of I1 equals 1.0 amperes in the positive y direction. The wire on the right is located at x equals positive 10 centimeters, carries a current of I2 equals 2.0 amperes in the negative y direction. Calculate the magnitude of the magnetic field along the line that lies halfway between the two wires at
that's our answer for part A of this question. Yay, good job everyone. Part B. Calculate the magnitude of the magnetic field along the line at x equals negative 20 centimeters, located 10 centimeters to the left of the wire carrying current I1 and 30 centimeters to the left of the wire carrying current I2. Give your answers in units of microtesla. To draw the diagram, so we have current acceleration equals 1.62 times 10 to the 13th power meters per second squared. We're solving for theta. We're going to use F equals ma. The force equals mass acceleration. F equals qvb sine theta. Okay, we're gonna isolate sine theta, putting everything else on the other side of the equation, or on the other side of the equal sign. Plugging in our information. 1.67 times 10 to the negative 27th kilograms times 1.62 times 10 to the 13th power meters per second squared divided by 1.6 times 10 to the negative 19th coulombs times 500,000 meters per second times 1.18 Tesla. Plugging that into our calculator. We get, I'm just gonna write 0.287. Now we're gonna take the inverse of sine in order to find the angle theta. Okay, 16.7 degrees as our answer. Next it says consider the network of 6 resistors shown in the figure below. Find the value of the single equivalent resistor that could be used to replace the entire resistor network. Assume the following values for the circuit elements. Okay, so we'll begin by combining RA and RB in parallel. So we'll have 1 over REQ equals 1 over RA plus 1 over RB, where REQ equals 1 over 3.0 ohms plus 1 over 6.0 ohms. 1 REQ. Multiplying the left side by a circuit will look like so. F 2.0. equals